Okay, so in this video, we're going to talk about slope fields, some nomenclature of differential equations, ordinary differential equations in the context of your knowledge of Calculus 1. And our primary objective is if you're given a differential equation, can we determine a visualization of a particular solution? And how could we even verify if we had a solution? So those are the things that we're trying to determine in this little lesson. So I'm going to get a couple different definitions here. Differential equations is a whole branch of mathematics that there are textbooks on textbooks written about this particular field. There's lots of acronyms and a lot of nomenclature vocabulary. And in your first exposure to calculus, as you start to complete your one-dimensional training, differential equations is typically used as a way to just, how do we analyze separable first-order differential equations, or possibly visualize a differential equation using a slope field, which effectively are small isoclines, iso same, and so same lines by using your differential equation that determines your slopes at various points in the particular domain or x and y plot. So definition, any equation that involves a derivative of a dependent variable with respect to another independent variable is called a differential equation. So it's called a differential equation. So if you see an equation that has a derivative in it, we call that a differential equation. We name it how it is. An algebraic equation is something that simply only has algebraic symbols and not derivatives in there. If you saw integrals in an equation, you would call it an integral equation. Later on, when you start to learn your multivariate calculus, you learn that there are partial derivatives, and we can have equations with partial derivatives, and we call those partial differential equations. So, but for this context, if you see an equation that has a first derivative or a second derivative with respect to a variable, that's a differential equation. We say the order of a differential equation is the highest order derivative that you see. So if I'm looking at the equation and I see a third derivative being taken, and that's the highest order derivative in the equation, we say this is a third order differential equation. So it's always dictated by the highest order number. The acronym we often use for differential equations is DE, differential equation, or sometimes ODE, meaning ordinary differential equation, because they're just ordinary. There are also, of the context of ordinary differential equations, there are a whole bunch of categories of boundary value problems, initial value problems, nonlinear differential equations, but you'll see this acronym often, ODE. We love TLAs, so that's why we didn't call it just a DE. And an ODE, in a dependent variable y, has a solution if there's a function that satisfies the ODE. That's all we're looking for. Just like if I gave you a quadratic equation, we're hoping to see, is there a number that satisfies that equation? In here, we're just looking, is there a function that satisfies the differential equation? So here's a differential equation, okay? It's a second order differential equation because the highest order derivative is 2, y double prime of x plus y of x equal to 0. And I just want to show that y equal x squared is not a solution. And so to show it's not a solution, we're going to take two derivatives of y and add that to the original function. If that sums to 0, always, then we would say it's a solution. Now, if we take two derivatives, so the first derivative of x squared is 2x, the second derivative is 2. If we were to plug that into the differential equation, the second derivative is 2, add the original equation, so it says take the second derivative and add that to the original equation, you get 2 plus x squared. And that does not always equal to 0, and therefore y equal x squared is not a solution. But sine x is a solution. Look, if we take the derivative of sine x, which is cosine x, and we take the second derivative of cosine x, which is minus sine x, and we plug that into the differential equation, second derivative is minus sine x. We've got to take the second derivative, we're going to add that to the original equation, which is sine x. That always sums to 0. And so sine x is a solution to that second order differential equation. But you know what? 21 cosine x is also a solution. Okay, do you know 19 and 20 recently got in a fight? 21. 21 cosine x is a solution. Let's check again. Y prime is 21 sine x, or minus 21 sine x. Okay, and y double prime is minus 21 cosine x. And if you add the second derivative to the original equation, minus 21 cosine x plus 21 cosine x, that always sums to 0. That means that's a solution as well as that solution. There are more than one solution to this second derivative or second order differential equation. So we might say, what's the general solution? Can we write down the full solution to the problem, which is a combination of all of my solutions? And so we say the general solution somehow encapsulates the full set of all possible solutions. In this case, I'll leave it as an exercise to verify, but all the solutions here are possible constants times sinusoids plus constants times other sinusoids or cosines. So if you want to look at to verify this a solution, just take the derivative and then take the second derivative, add them together, and you would show that that is a general solution to that second order differential equation. So if you have a differential equation such as this, and you have to verify the solution, and you're given a function, it really is a piece of cake. It just really depends on, can you take the derivatives using your rules, product rule, quotient rule, chain rule, implicit differentiation could be one as well. So we just really have to plug and chug, okay, to verify solutions. One of our prerogatives, of course, is that wouldn't it be really nice to not have to be able to generate solutions if you're given a second order differential equation? Could I determine that this is the solution if you're just given the differential equation, because I gave you what the solutions were? That would be a really interesting thing to be able to answer. Okay, so if we look, a general solution to an ODE does have unknown arbitrary constants. And look what we just had. We had a second order differential equation, and you ended up with two independent solutions. I'm not going to define what I mean by that word independent, but there are two very different solutions, sine x and cosine x. These are two different functions, but there's two arbitrary constants there. It turns out the number of arbitrary constants is always linked up to the order of your differential equation. Now, for the most part, for your experience in Calculus 1 in getting exposure to differential equations, we're going to deal with first order differential equations, which means we're often going to have just one arbitrary constant. But I want to put a ODE or an ODE with initial conditions can be used to determine constants and obtain a specific solution or a particular solution. So I want to go back just for a second here. If you actually knew a condition, if you knew a location where the solution passed through this point, or it was at a moment in time, then you could pin down what that arbitrary constant is. We call those conditions. So if it's given to you at an initial time, then we call it an initial condition. Sometimes the conditions could be at a later time, or they could be at different locations in space. And so we might have boundary conditions. But they can be used to determine those constants. So here's an example. Suppose I have y prime is equal to 2yx. We're going to learn in another video that this is an example of an exponential growth model with a growth factor of 2. The general solution to this, I'm going to write down, is y is equal to a constant times e to the 2x. And you can verify that by direct calculation. Take the derivative with respect to x, and you get 2c e to the 2x. And that would equal to y prime is twice the original function. Okay. if I gave you, suppose y of 0 is equal to 7. Suppose this function actually passed through the location y of 0 equal to 7. That's an initial value. So we often would call this differential equation an initial value problem. So another TLA, IVP. But we could use this to determine that C value. Let me use a different pen here. Oop, I hit the other one. So for instance, if we plugged in x equal to 0, we would get C times e to the 0, which is equal to C. It would say C is equal to 7, and we then have our particular solution, 7e to the 2x. That would be our particular solution. This is our general solution. There's our particular solution because it passed through a particular point. Okay. Now, the forthcoming sections is looking at how do we find these solutions if you're given a very simple differential equation, which are going to be called separable differential equations. But if you were given the general solution and you knew it passed through a particular point, then you could find it was very specific or a particular solution. But a side goal of this section is that, especially because oftentimes we don't know how to find the general solution, but we do have the differential equation. And the differential equation could have came from a mathematical modeling of a particular physical situation and using, say, Newton's second law, your balance of forces, and that equal to your mass times your acceleration. You already know acceleration is twice your position functions, or that's your second derivative of your position function. And so we might have to have a way of generating a picture of what the differential equation looks like, because this is a derivative function. It tells you what the slopes are at every location of x and y. So here's the idea. Okay. First, remember the derivative just documents the slope of a tangent line to a function. Okay. And a solution to a first order ODE will always have one constant. Those are our 2 bullet points. And the idea is here. Okay. We can use the ODE to figure out the slopes. And then we could picture those little tangent lines in the space x and y. So if you're given y prime as some function of x and y, then if I told you I was at say 0, 1, then I could figure out what the slope is of a tangent line at 0, 1. And then I can make a picture of those slopes by a little small line segment that really is that tangent line. And that will give you the direction or the flow of that particular, at that particular location. So let me give you an example of it. Okay, so I'm just looking at a textbook here. This is a textbook written by Rogowski and Adams, Early Transcendental Calculus 3rd edition. This is a textbook that we use here at Stephen F. Austin State University. So I want to look at just an example of this. So suppose you have this differential equation. dy dt is equal minus ty. At this point right now, in your knowledge, you may not know now how to solve this differential equation. But what we could is we can make a plot of t and y, and at every location here, we can figure out what the slope is of the tangent line. So at t equal to 0, if I plug in t equal to 0, dy dt is always equal to 0. That means the tangent line must be horizontal. So I got horizontal tangent lines. Every single location on the y-axis is a horizontal tangent line. But think about if you're a little bug right here, and I was traveling left to right. This says I'm going to go off that way. And you could then evaluate the derivative again at a very close point. So like right here, if I let t be a little bit greater than 0 and y is a little bit less than, say, 4, then dy dt would also be a little bit less than 4, but it'd be negative. And so we'd have these slopes. And these are the slopes that are evaluated at all these different points using my derivative function. So just as another example, if I let t equal to 1, t equal to 2 and y equal to 1, plug that in here, it says dy dt is equal minus 2. And so I'm going to make a line with a slope of minus 2. And we could think about flowing through that curve, and that could give me a trajectory, a possible solution to this differential equation's path if I were to start at its location. Now you can think about filling up this entire domain T and Y with all these short little line segments that all indicate the tangent line at that particular point, and you might get a picture like this. So I'm going to zoom in a little bit more, okay? This is the slope field for the function minus ty. So this is, remember, it's y prime is equal to minus ty. And all these little line segments are the slope that's been generated by this function at particular locations. So in the book is identified at minus 1, 3, dy dt is equal to 3. And so that's why I'm going to write a small little line segment with slope 3. And you do this for this entire picture, and you can start saying, well, if I was living right here, I could follow along these lines, and I can get an idea of my shape. That's the idea of a slope field. So let's do one last example before you get off into doing your homework for section 6.1. Here are two different first-order differential equations. dy dt is equal to t squared, and dy dt is equal to y squared. You'll learn later how you can solve this latter one. This one you might be able to find with our knowledge of antiderivatives. You can just, the antiderivative was 1/3 t cubed, okay? But what I want, remember, the antiderivative would be 1/3 t cubed plus an arbitrary constant. That constant is specified by figuring out where you are in the curve. Now, let's look at this. If t was equal to 0, dy dt is always equal to 0. So I should have a horizontal tangent line everywhere along the y-axis. And as t increases, dy dt becomes more positive, and so I should see it getting steeper and steeper and steeper. In fact, t squared is always a positive definite term, and so every location I should have a positive slope. So we see that this graph right here is actually dy dt equal to t squared. In contrast, if you look at this one, if y is equal to 0, then I should have horizontal tangent lines. As you increase y, I should see dy dt get steeper and steeper and steeper. And that's exactly what you see over here. And so this slope field is generated by here. Now the goal for most of us is, if you are given, especially for your calculus students, is if you are given a particular graph of a slope field, could you match that to a particular differential equation? Or if you're given a differential equation, could you draw a few different slope fields as well? That process may be tedious, but you just have to take enough points in here to kind of get an idea of the trend. I would recommend first look at what happens when y is equal to 0 or t is equal to 0 to get that idea. Then increase t and see what happens. Decrease t and see what happens. So hope that helps. Get into your 6.1 homework, looking at slope fields and verifying solutions to differential equations.